think about the synthesis route for the final compound here from the starting material. So I've given you some help here, right? So you should proceed from this to this via the following intermediates. So you just have to look at this and just connect this to this, correct? So how do you get from here to here? You have one double bond and you want to form two double bonds, correct? So the way to do such is actually quite straightforward, right? And there are a lot of ways to do it, and there's not really the best path, right? Since all roads leads to Rome. So what I will do is that, taking this double bond, I've learned in alkenes that if I throw in liquid bromine, right, I'll get the electrophilic addition occurring, and I have these two with Br. And in order to get this double bond, I just have to perform a dehydration, dehalogenation, correct? So you already learned this reaction in Rx, right? What's the condition that you should use in order to achieve the transformation?
Ethanolic sodium hydroxide.
Is it? Yes, okay. So you will use ethanolic NaOH and reflux. So now the question is, why wouldn't they form this? And then later, let's say, form this, a triple bond. Because by your Sayzeff's rule, correct? The most substituted alkene will be formed. This is not the most substituted alkene. This is because you will generate a tertiary alkene here on both ends, right? So therefore you will get this product instead of the alkyne, which is the triple bond. So first two steps settled, right? So you reach this stage. So now in order to get to this, it's quite obvious that you must somehow do an oxidative cleavage to break the center bond, right? And you have learned that in order to do oxidative cleavage, you use, what should you use? Hot KMNO4, right? Of course acidified, and of course reflux, right? Or you just put KMNO4 H plus reflux, right? It's the same thing. So after this, you will generate this product. And this part will become CO2. This is one of the special structures, correct? So now you are getting closer and closer to your final product, which is this. And then in order to get from this to this product, what should you do? Remember, there's a methyl group here, correct? And the rest of the structure, basically, there's no change. So now you're only concerned with these two. So how do you convert a ketone to a carboxylic acid? This is the part whereby a lot of people will stumble, right? Because in fact, a lot of students will say that they have never learned this reaction before. But yes, they have learned this reaction before, but it's in another form whereby the students have never thought about this, right? You actually use I2 and NaOH, which is your iodoform test. A lot of students miss this out because they think that it's a test but not a reaction, but in fact it's also a reaction, right? So this will give a positive test for this type of structure, like what I mentioned the other time. So now you will be oxidized to your carboxylate, and this part will be still your ketone, because this only react with your special structure, right? So after you reach this stage, you're getting closer and closer to this, correct? So in order to get to this, what should you do? You should reduce your carbonyl to become an alcohol. So what should you use to reduce it? You can use your NaBH4, or you can use your H2 nickel, right? But not lithium aluminum hydride, because that will reduce this as well, right? Later on we'll see what reduce what, right? So either one, you will have the carboxylic acid plus your alcohol. And this final stage, this one you should know, right? Con H2SO4, and you'll get a final product. It will be hard if I don't give you this and tell you to think of a path directly, right? But this should simplify the problem. Okay, so this is the way to do such a question. Of course, there are other ways. You can always think about other ways, right? Next one. Again, another synthesis type of question. So for part A, the question say that you actually use a reagent C to form compound B, right? Here shouldn't be reagent B, sorry. Here I should have labeled this reagent B, right? But it's okay. So now you know that the succinic acid is this part. It's quite obvious, correct? So succinic acid must have reacted with these two alcohol to form this. And it's quite obvious that this is an esterification reaction, and you have learned the reaction conditions, which is your con H2SO4, right? Here under reflux. So the problem comes with this part. So now it says that when reagent C reacts with excess sodium hydroxide, 2 equivalents of AgNO3 is required for the formation of the white precipitate. So based on the keyword white precipitate, you know that it is AgCl, right? And when I tell you I require 2 equivalents of AgNO3, you know that there are 2 Cl, these kind of structures within your reagent C, right? So this tells you that your compound C should contain 2 Cl groups, right? And then you look back into your structure. Now in order to form an ester from this phenol, right, what is the only thing that you can introduce? That is your acyl chloride. Because only acyl chlorides are reactive enough to react with your phenols, right? I mentioned the other time phenols are less reactive, so they don't react with your carboxylic acid. So you need a acyl chloride. But the problem is, where is the other Cl, since there's 2? Now you look at this structure again. On top of forming a ester bond, you're actually forming another bond here, right? Now if I just tell you to ignore everything, treat this as a phenol, ignore everything, treat this as this part, right? How would you form a CC bond on the ring? This is a reaction which you have learned, which is your Friedel-Crafts alkylation, right? If you can still remember, you are using the ring, right? And you can connect an R group by using RCl and AlCl3, right? So now you are basically doing the same thing, just that you are performing your esterification and your Friedel-Crafts alkylation together, right? And based on this structure, you should be able to deduce that the other part must be, here, 1, 2, 3, must be like that, right? So now you will have this as your reagent C, right? Whereby this part will form the ester, this part will form the ester, and this part will be responsible for your Friedel-Crafts alkylation. Okay? So a simple test to distinguish reagent C and reagent B. This is quite easy because of the Cl. In fact, I already told you the answer here, correct? You can just use AgNO3. This will give you a white precipitate, this one. You can use other fanciful methods, right? There's a variety of methods. But this is the most straightforward, right? AgNO3. So next, suggest a synthesis route for compound B from compound A, making use of only succinic acid and reagent C as your organic reagent, right? Like what I mentioned the other time. Like what I mentioned just now. You can just take this, right? Throw in your succinic acid. And of course your con H2SO4, right? Before you finalize your answer, you must look for any side reactions that may occur, right? For this, not really, right? Like what I mentioned, phenol doesn't react with your carboxylic acid. So this is going to be quite safe to generate this compound. which is your compound B, right? And what you do next is that you can just throw in your compound C, right? For this, remember you need to deprotonate your phenol first, right? Because like what I mentioned, phenol is not that nucleophilic because the lone pair is delocalized into a ring, right? So therefore you introduce sodium to deprotonate it before you throw this in. So after you throw this in, right, I won't draw this part, the left side is the same. This is what you get, okay? And the final step is just to add AgCl3 and a Friedel-Crafts alkylation will occur, right? And you get a final product. So now, can I swap these two? Can I, let's say, add reagent C, which is this first, to this side, before I add succinic acid to this side? What do you think? Does it work? Remember, always think about any side reactions that may occur, right? So now, this is the answer. If let's say I were to change the order of these two steps, right? I'll add a reagent C first, right? What do you think will happen? You know that you can form ester using this, correct? But the thing is, if you compare this alcohol with this phenol, which one is more nucleophilic? It will be this, because it's not delocalized, while this is delocalized. So since this is more nucleophilic, it makes sense to think that this will react with this to form this ester, right? And this will be just like that, and you will not get your final product, right? So you cannot swap the two steps, right? Now what's another lesson learned from this reaction, right? If let's say you have a phenol and you want to form this compound, let's say like that, right? Usually such reactions will not occur if you just add RCl and AlCl3. Do you know why? Do you know why will it not occur?
The OH group is deactivated.
No, OH is activating, remember? OH activates here, here and here. And activates the 2,4 position. Right? So since it activates here, here and here, by directing the RCl, by directing the R group to this position, there will be less steric hindrance compared to these two positions. In other words, your major product that you will obtain, right, will be this product instead of this product. So we're actually using the above method to direct it to this position, because after, if let's say there's a group that can bind to your OH, right, you can bind to OH first and gets restricted, right, such that you can only substitute here or here instead of this position. And afterwards, do you realize that you can just perform a simple hydrolysis and then you have two parts already, right? So you're actually using OH to help you to direct it to this position, right? There's another area chemists like to explore by using directing groups to direct it to a place where they want, right? So next, suggest in no more than 3 steps how succinic acid can be obtained from 1,4-dimethyl-cyclohexane 1,3-diene, right? So if you draw that structure, this is what you get. Okay, so this question is just asking how you can obtain from here to here, right? So same thing. This is pretty much like the first question. You have to perform a oxidative cleavage. So after you perform the oxidative cleavage, you get a diketone, 1,4-diketone. So after you obtain this diketone, in order to go from here to here, right, what you have to do is, again, I2NaOH. So this, which is your special structure, will be converted to your carboxylate. Same thing for this side. And the last step, you can just do a protonation with a suitable acid. Right. So this is your KMnO4 acidic heat. Right. A very simple 3-step synthesis. So please pay attention to this structure, this reagent, right? The next part, epoxidation. So it was mentioned that you can perform epoxidation with these two reagents, NaOH or Na2CO3, and you have 80% U in 3 minutes for the first one, 80% U in 45 minutes for the second one. So based on this observation, you know that the rate of reaction is faster for the first one than the second one, right? So now I ask you to suggest the role of your NaOH and Na2CO3. Is quite obvious that they are acting as a base, right? NaOH is a base, Na2CO3 is a base. But your NaOH is a stronger base than your Na2CO3. You have learned that already. So now, based by examination of the amount of time taken for 80% U, describe the reaction mechanism. So now, if I throw in a base, the most obvious thing to do is to find the most acidic proton, right? For here, for this kind of structure, there's only one, which is this proton. So if you add in a base, let's say NaOH, right, you will deprotonate this alcohol first, and you form this alkoxide species. This is just your acid base that you have learned, right? And you might wonder, NaOH, you have learned that is not a strong base. It's a base that's not strong enough to deprotonate alcohol, correct? But that's actually false, because when we talk about acid base, we talk about equilibrium, right? And we talk about equilibrium, there's no such thing as it will not deprotonate. Just that maybe the percentage of this ionized might be little, right? But it can still occur, right? So once you obtain this species, what happens next is it performs a SN2 reaction. Now, why is it SN2 not SN1? The reason is very simple, right? The clue is given away here. If it's an SN1 reaction, changing the base will not change the rate, right? Because the rate of formation of these will have nothing to do with your rate of your overall reaction. So therefore, this statement tells you that it should be an SN2, because the stronger the base you use, the more this is deprotonated. The more this is protonated, your SN2 reaction will be faster. So therefore, it is an SN2 reaction, right? So you can draw your partial positive and negative charges, and you obtain your epoxide, right? Very straightforward. Of course, you can plus your Br minus plus your H2O, right? Now, another reason why students don't really understand why this can deprotonate this is, right, I can use this to explain, right? If let's say you have, I simplify it, you have this alcohol, right? Of course, you have learned that NaOH is not able to deprotonate it. In other words, if I add in NaOH, the equilibrium will be like that. This side is shorter, this side is longer, right? However, for the second step, it is irreversible, right? So this is your product, this is irreversible. So does it make sense to think that eventually everything will be converted to a product no matter how long this equilibrium arrow is, correct? Because these two exist in equilibrium, and once you reach this, you'll form the product. So eventually everything will form the product no matter what base you use, just that the rate might be slower, right? So don't just think that this is weak, it doesn't react with it. Yes, it reacts, just that the equilibrium is not very favorable, right? So now, Yeah, why there's a difference is because this is a stronger base, right? Hence, or otherwise, draw the energy profile diagram for epoxidation. So same thing, starting you have this epoxide, right? This is testing a concept, not memorization, so don't just reproduce whatever that's in your notes, right? Remember the first step, you even drew the first step as deprotonation, so you should account for the deprotonation step as well, right? So now, if I were to deprotonate, of course, every reaction has a hump, right? And an intermediate. So this is the intermediate, which is at this stage, right? So this is your intermediate. And afterwards is an SN2 reaction. For SN2 reaction, you know that there should only be one hump, right? So this is your transition state for SN2 if you want to draw it out, right? Why is this hump greater than this hump? Because like what I always emphasize, acid-base reaction is always very fast. So therefore the hump is slow. It is lower than your second hump, right? So you just have to fill in your products, right? And this will be your energy profile diagram. So be flexible, right? Don't just always draw one. It can be 3, it can be 4. Next one. It was discovered that only one of the stereoisomers formed the epoxide while the other didn't form, right? So this is testing you on stereochemistry of SN2, right? So for SN2, you have learned that if let's say I have an X here, right, have a nucleophile, you will perform a backside attack to kick out the leaving group, correct? So for this, it's the same thing, right? Just that I make it into one structure. So let's say we deprotonate the second one. Right, this is what you obtain. Now if I perform the attack, is it considered a backside attack? Or a front side attack? It will be considered front side because both are pointing the same side, correct? For this, these two are pointing the opposite sides. So this will not react with your, this will not react, right? Will not epoxidate. So now if I were to change this to dash bond, yes, this is pointing in the opposite direction. So of course it can perform a backside attack, right? Which means you only form an epoxide for the first one but not the second one, right? And your epoxide is very easy to draw, it's just like that, right? And just for info, there's no such thing as like that. Because you have a 3-member ring, there's no way for you to point one up and one down, right? So this is the structure for the first one. And then for the second one, it was discovered that for the other stereoisomer, which does not undergo epoxidation, another product is formed, right? So draw the product for the one that did not undergo epoxidation. So for this is actually this product, which is a elimination product, right? Because NaOH acts as a base. Another way can, another answer that is acceptable is this, right? Whereby it performs a SN2 reaction. Either one is fine. Because I also never specify what's the solvent or whatsoever, right? Just think of the stereochemistry, that's all. Okay. So let's try some questions. So let's try the first question. remember, in order to compare acidity, first step is always deprotonate it, right? And then you compare stability of the conjugate base. So why not tell me which one is the least acidic? Which one is the least acidic?
The one on the right.
The first one? The one on the right? Least acidic. Why is it the least acidic?
We all said the other way around. You know.
I was thinking, is it because like it's like the negative charge is dispersed over a smaller area?
For the first one?
Yeah,
Why is it a smaller area?
because it's closer to the.
Shouldn't closer be stronger? So first, NO2 is an electron withdrawing group, right? So now instead of usually the question asks about different substrates, but now we are comparing the same substrates, just that they are at different positions. So this actually, this question is actually related to your Arins chapter, right? So now, let's talk about this, right? We know that, okay, don't talk about this first. So we know that NO2 will direct incoming electrophiles to which position? Can you still remember? NO2 is an electron withdrawing group, so if let's say I have an electrophile, the electrophile will be attracted to which position? It will be the 3, right? 1, 2, 3. Which means here must have negative lah. Negative, negative. Right? That's why this is attracted here. Which means the other 3 positions must be positive, positive, positive. So there's higher electron density here, less electron density here, right? So I just erase away the negative. Now if let's say I attach an O minus here, right? Do you think this will be more stable or this will be more stable? Which one you think will be more stable? This one or this one? The one on the left, correct? Because now you have positive charge to neutralize this. For this, no, you're actually intensifying the negative charge because there's partial negative here, which means that this should be the least stable. Least stable means least acidic, right? So we already found the one which is least acidic. Okay. Another way is you use resonance structure to draw it, right? But understanding this way is good enough already, right? And let's look at the other one. So now here's our headache. Where our headaches come from. Put the O minus here, right? If you were to compare these two, both of them are at plus plus, right? So which one is more stable, this one or this one? The answer now comes from the distance effect, right? I believe you all have learned carboxylic acids, correct? So they already given you this example whereby they say that, okay, this versus let's say this, okay, and then this will be more acidic because F is closer. So the reason is the same. Your NO2, which is an electron withdrawing group, is closer to this than to this, which makes this more acidic, right? So this will be the most acidic. So you have to, for these two, you have to compare distance, while for the other one, right, you have to compare the resonance effect or the electronic effect, right? So you can go on by saying that NO2, which is electron withdrawing, right, withdraws electron density from the second and fourth position, right? Like what I mentioned here, since it withdraws at second and fourth, there will be partial positive, right? And then, alright, NO2, which is the electron withdrawing, withdraws electron density from second and fourth position, right? Thereby causing these positions to have a partial positive charge. So the positive charge can stabilize adjacent negative charge after the corresponding phenol have been deprotonated. Right, this is for the comparison of this and the third position, right? And then between these two, you can just say that this is closer, so there's a stronger inductive effect, right? Take note, NO2 can be both inductive and electronic, right? So there's electronic effect, there's resonance effect because it's attached to a ring. There's inductive effect because this can withdraw electron density via sigma bond, right? Like what I always mention, inductive effect is by sigma bond, resonance effect is by pi bonds, right? So for this, you can see that there is a strong resonance effect, but weak inductive effect. But for this, you have a strong resonance effect and a strong inductive effect, right? This is another way you can you can compare or complain. And for the third position, there is no resonance effect and there's only weak I, so therefore it is the least acidic, right? Okay, let's look at the next question. have this diol and you add in PBr3, you know that one of the OH is going to be converted to Br, right? So the question is which OH? So if you were to make a random guess, let's say this OH, right? So if let's say this is compound B, and then you throw in a base for step 2, right? If you throw in a base, same thing, this will be deprotonated. And in order to get that product, you know that it has to perform a intramolecular reaction, right? Now, if this reaction is an SN2, your final product will have this being a wedge, because it will cause inversion, right? Now, if it's an SN1, you will not have a dash, because that will lead to racemization. You have two products, right? So since there's only one product, you know that it cannot be this that's being deprotonated, that's being left out, right? So it must be this. So now you swap these two, right? This will be your PR. So this is the only acceptable answer for compound B, right? Another way why this is being converted instead of this is because this is less sterically hindered, right? You have two groups, one is a secondary alcohol, one is a primary alcohol. The primary alcohol will be more reactive because it's more exposed compared to a secondary alcohol. This is another reason why this group reacts, right? Anyways, after you obtain this, then for the second step, right, you throw in a base, you can just use B minus to abbreviate it, right? This one doesn't matter. Same thing, you'll have your O minus, right? Afterwards, it's just a SN2 reaction, since this is primary, and you will have your final product plus your Br minus, right? Relatively straightforward as well. And for 3, do you have a synthesis? There's a problem with this step, right? So for the third question, you have an alkene and you want to end up with an alkene. Of course, you know that you cannot just go around the reactions involving alkene, because there's only like one reaction they have learnt, right? And you have, since you have only learned one reaction, you should use that one reaction for your alkene to functionalize it. So now the first step is quite obvious, that you have to perform a free radical substitution, right? There's no other reaction that you can do. So for this free radical substitution, right, you can either draw the PR here or your PR here, doesn't really matter, right? Either one will give you your final product. So I just draw it here, right? So now I've already given you a hint as well, which is to introduce an alkene, right? So you should know that in order to introduce alkene, I should use a base, right? So KOH, ethanol, right? Reflux. So I will have this alkene. And next, since I want to perform this reaction, right? Let me see. Sorry. For the first one, you should obtain this product, right, as the major product. But it all depends on what is your argument, right? Because like what I mentioned, a tertiary radical is more stable than a secondary radical, right? But for this, you have 1, 2, 3, 4 times higher than this. So it depends on which one the overall is higher, right? So you may use this reaction or you may not use. That's why I say hence or otherwise. I never say you must, right? So now I just draw this way. So if you have a Br here, you form same thing, a double bond, the most substituted double bond. Right? If I form the double bond here, I will have a di-substituted double bond, which is not as stable as this tri-substituted double bond. So I'll obtain this. Right? Now I can use the reaction that's proposed here because I want to functionalize this. Right? If I just add a HX, let's say, my H will add here and my X will get back here. So it doesn't really help me. So what I want to do is I use the proposed reaction 9BBN followed by NaOH H2O2, and based on the example, right, and apply it here, I should get this, the anti-Markovnikov addition, right? So after I obtain this, how do I obtain the final product? Now you have to think about it. So for the final one, I have one additional carbon, right? How do I introduce an additional carbon into my structure? What reaction have you learned whereby I introduce an additional carbon?
You replace it with nitrile. Replace it with nitrile.
Nitrile, yes, correct. But can I just add nitrile NaCN directly? I can't, because OH, like what I always say, is a poor leaving group. So you have to convert it to a good leaving group by using your PBr3 or PCl5 or SOCl2, right? So after I add this, I should have the corresponding X here, right? Depending on what I use. This one doesn't really matter, right? So then I can introduce my NaCN, reflux whatsoever. And now I have a step-up reaction whereby I have an additional group here. And I introduce your C. So now I just have to think of how to get rid of this N. Right? So how do I get rid of this N?
Hydrolysis.
Yes, I can perform a hydrolysis, right? After hydrolysis, I'll have my carboxylic acid, right? This is just H2SO4 reflux, right? Just always remember, right, the most useful functional group is your oxygen groups, because oxygen groups can be converted to a lot of things: alcohols, ketones, aldehydes, carboxylic acids, esters, etc. Right? So they're actually very versatile. So what I want to do is we want to try to converge everything to an oxygen functional group, right? Because since oxygen can be converted to basically everything within 1 or 2 steps, it's very useful, right? So after we obtain this, what I want to do is that I can just reduce it with lithium aluminum hydride, right? So after the reduction, I'll have an alcohol group here, right? So now we are getting closer and closer to the product. So in order to get to this, right, you just have to perform a dehydration to form a double bond, right? So this dehydration, can you still remember what is the, sorry, this elimination, can you still remember what's the condition?
Excess corn H2SO4.
Yes, right, excess corn H2SO4, and you heat.
170 degrees.
Yes, or you can use Al2O3, which is a dehydrating agent, right? Either one is fine. So after you obtain this, you can just reduce it, right? H2 nickel, and you have your final product. Although this synthesis looks simple, but you involve a lot of steps, right? So if the Br is at the other position, right, you can just go from here to here directly, right? So it's just 1, 2, 3, 4, 5 steps, right? If you are smart enough to think of the Br being added here, you should be smart enough to think of this longer path, right? If not, you can always do a shorter path, doesn't matter. Okay? So these synthesis questions actually helps you to think a lot, right? So let's try question 4. And of course in real life you don't do such. There are reactions whereby you can get, let's say from here to here in one step, right? Just that you haven't learned yet. You really have answer? It should be quite easy, right? Since it's one star. Answer is A, right? Since you have NaOH, which is a base, you will deprotonate your phenol and as well as your carboxylic acid. And for the ester, you just perform a hydrolysis to form the carboxylate. Right? It's not much of a issue here. So if you're okay with that, you can go on to question 5. So like what we mentioned, phosphorus pentachloride doesn't react with your phenol, correct? Because for this reaction, your O is actually acting as the nucleophile. But for this O, the lone pair of O is being delocalized, so therefore it doesn't happen, right? So same thing, like what I said, your enols react in pretty much the same way as your phenol, right? So same thing, this lone pair is delocalized into the double bond, so therefore there's no reaction for this as well, right? So you only react with those aliphatic alcohols, so there's a total of 3 inside, right? Next, 2 mole of hydrochloric acid at room temperature. So the first mole of hydrochloric acid will react with your amide, right? There is an amide there. And how many moles are required to react with amide? If let's say you have this, correct? And you react it with HCl, you know that you obtain carboxylic acid plus your NH3Cl, right? So how many moles of this is required?
Just one.
Okay. And then you have your amine plus your HCl. You will have your tertiary salt. right? So now you have 2 moles of HCl reacting with it at room temperature. And the last one, 6 moles of ethanol chloride. So for your ethanol chloride, you know that it reacts with your phenol as well as your alcohol, right? So this will react with basically all the OH, right? 1, 2, 3, 4, 5. And take note of the amide, you also react with, and take note of the amine, you also react with your amine, right? Since this reacts with your alcohol, right, and you know that amines are more nucleophilic than alcohol, therefore it should react with your amines as well to form amides, right? You have learned carboxylic acid derivatives, right? So you should know this reaction as well. This plus this, right? You obtain your amide. Okay, so react with 6 moles of your ethanol chloride as well. Sorry, this should be like that. Okay, so this is basically testing you on this concept, this versus this, right? So a lot of students just neglected the other one. So let's try question 5, question 6. So consider all the structure isomers of C4H10O, right? So for C4H10O, how do you calculate how many double bonds or rings there are? I've told you this method, right? The double bond equivalent. So you can use that method to calculate, right? 4 times 2 plus 2 minus 10 divided by 2, you will get 0. So it's a straight chain. So C4H10, quite easy to draw as well. This is C4, so you can just add OH somewhere, right? Since you know it's not an aldehyde or ketone because there's no double bond. So you just have to draw all the possibilities. This is one, this is another one. And then you can start off by branching, right? So this is one, and this is the other one. There's only 4. So hot acidified KMnO4, it will be all except the tertiary, 1, 2, 3, right? So A and B are out. Next, alkaline equals iodine. You must have that special structure, and that in order to have that special structure, you have this structure, right? And this is the only structure. Any metal, of course, will be all 4, since doesn't matter whether you are primary, secondary, or tertiary, right? And then for question 7, I find it quite stupid, right? It seems that question 7 is going to be a hard question, right? There's a lot of data given, and you have to analyze. But pay more attention to the setup of the apparatus, right? Which one is the odd one out for the setup?
This one.
Which one is the odd one out? D, right?
Yeah.
Because the water in and water out is different, right? Basically, that is what this question is testing. And the answer is really D, right? For all the rest, the water in and water out is from different direction, and you should know why water in is from the bottom, right? If water in is from the top, by the time you reach the bottom, it is already hot already, right? So it's not as efficient. Although you still see people doing these kind of things in lab, right? It may affect their yield, right? So next, question 8. So this question pretty much tests on the same thing as the just now the E null question, right? So now I would prefer to draw it out this way. So first I use A equals NaOH. So if I use A equals NaOH, you know that this one of these will be converted, right? So this adopts a similar structure, right? As your, it's the same concept, right? This versus this. Right, both are not reactive towards your nucleophiles because of the same reason, delocalization. So therefore, only this Br will be substituted with your OH. Right? So afterwards, you add con H2SO4. This is your esterification. So you just have to link these two together. Sorry. So you just have to link these two together. Right? You will have a 1, 2, 3, 4, 5 member ring. So C and D are out, and beside the O there got a Br here, right? So quite obvious is B. Actually, this reaction is kind of redundant. You can in fact obtain the ester, right, just by using A equals NaOH, right? Why do I say so? Now imagine I have a Br here. Right? If I use A equals NaOH, we know that A equals NaOH is the base. Of course, you'll deprotonate the molecule first, right? So after deprotonation, this is what you get. You will not perform a nucleophilic substitution because nucleophilic substitution there will be definitely a slow step which slows it down. But for acid base, no, there's no slow step. So what happens now is this can just perform a nucleophilic substitution and you'll get the same product. You don't even have to throw in the acid. Right, you're wasting chemicals and you obtain exactly the same product, right? Right, question 9. look at the last option first, right? So the last option, is it a nucleophilic substitution? Now your nephtor is acting as a nucleophile, correct? And the other species is acting as an electrophile. So I can represent this reaction as such, right? You have a nucleophile, and then you react with an electrophile to form this species, right? What do you call this reaction? This is classified as electrophilic substitution, correct? So it's not a nucleophilic substitution. Okay? So if you want to explore more about the mechanism, this is known as a diazonium species. Right? So what happens is that, remember, this is your electrophile since it's positive charge. That's what's mentioned in the question. So what you do is that you will perform an attack, right? This part is something like a nucleophilic addition, right? Whereby you have a nucleophile coming in, and this gets pushed up to O. So for this, it gets pushed up to N, right? So after this pushing up, you have a smiley face here. The H will be here, and the 2 nitrogen, and the ring, right? Just use AR to represent, and this is what you obtain. So now remember, throw in OH minus as a base. So what the OH minus will do is that you will deprotonate this, and you obtain your final product, right? So for the second deprotonation step is quite obvious, right? Because like what I emphasized in arines, the second step is a deprotonation step, right? Depending on what I use to deprotonate. For this case, they use OH minus. So this is an electrophilic substitution reaction, okay? And then for C, it reacts with carboxylic acid to form ester, which is false because phenols only react with acyl chloride to form esters. And it doesn't give white fumes with SOCl2 because, like what I said, this CO bond is very strong. It doesn't break to form CCl. And next is pK is lower than that of a phenol. So same thing, when we compare pK, we compare stability of the conjugate base. So now you are comparing this versus this, right? So which one is more stable? It will be this, because now your negative charge is delocalized over 2 benzene rings. This is only delocalized over 1, right? So since this is more stable, you will be more acidic, right? And of course, I can have even larger ring size, right? This is your intracenol, I guess, right? Same thing, it is even more acidic than your nephtor, right? Because of the same reason. Then question 10. Answer A, correct? Quite obvious, right, this one? So both are SN2 reactions, right? This also gives you a preview of how the reaction occur. and how the changing of OH to Cl or whatever occurred. Right, for C, the rate of reaction for the first step is independent. Of course it's dependent because it's SN2. And lastly, water can be used as a solvent. Can it be used? You can't use, right? Why can't you use water?
So nucleophile.
Water is also nucleophilic, correct? That's one reason, but there's even one more obvious reason, right? We have learned in periodicity that if you use water with PBr3, something will happen, right? You will form an acidic solution. So that is also why you cannot use water in this case, right? So this year they really toned down periodicity, right, by combining it with the other two chapters, which is your group 2 and your group 17, right? So there's less things there, and they place a lot of things inside the data booklet, right? So you should use that to your advantage. Right, question 11. So proper 2 nor acts as a base. This is correct because H2SO4 acts as an acid. H2SO4 is regenerated, so it's a catalyst. Possible side product is this compound. If you were to look at the structure of this is just a reaction of your CH3CH3, which is your step 3, and your HSO4 minus. If let's say there's an SN1 reaction, right? So your HSO4 minus can attack your carbocation to generate this species, so it can occur as well, right? But for step 3, instead of acting as a nucleophile, your HSO4 minus is actually acting as a base, right? You know that it's acting as a base because this reaction only involves the transfer of H plus, right? So C is also correct. D, it is more likely for primary alcohols to proceed, which is false because for step 2 you know that a carbocation is generated, and you know that primary carbocations are unstable. So tertiary alcohols will undergo this reaction more, to a higher tendency, right? Question 12. I think bio people like this, right? This is your GPP, right? If I'm not wrong. So your isoprene units will join together to form your GPP, correct? Do you have to learn like how your isoprene join together to form your GPP and then form your what? Squalene?
I don't think so.
Don't think so. Or you all haven't learned yet? Learn already, right?
No.
You all don't learn cholesterol, all that.
We don't learn the structure, the raw structure only.
If you look at biology in a chemistry way, you realize a lot of things are, if you're good in chemistry, a lot of things can be explained very easily, right? All your biological processes, in fact, they involve mechanism also, right? Any difficulties? I think there's a lot of difficulties, right? So you just have to follow the steps, right? So in a concerted manner, the CO bond breaks, which is this bond, right? Then you can have a water, and a carbon atom is attacked by an electron-rich double bond, leading to the formation of a carbocation of a 6-member ring. So this is your, you can see that this is a combination of your electrophilic addition and your nucleophilic substitution, right? The nucleophilic substitution part is here, whereby your alkene is acting as a nucleophile. The electrophilic addition part is on your alkene, right? So you just have to count 1, 2, 3, 4, 5, 6. In order to form a 6-member ring, this double bond must attack here, right? So this must attack here. I'll prefer to write it this way though, right? Because drawing from a double bond attacking here, it can be either this carbon or this carbon, right? So it should be this carbon, right? So after I attack it here, I will form a 6-member ring. If I'm not sure, can same thing, number them 1, 2, 3, 4, 5, 6, right? So between 2 and 3, there's a double bond. On 3, there's another methyl group. 4 got nothing, 5 got nothing, 6, right? There's this group attached. And I know that after I perform an electrophilic addition on this carbon, there should be a positive charge here, right? So this part is something like that, right? Originally I have like that, let's say, and then react with attack somewhere. Since it's this carbon that is doing the attack, I'll have a positive charge on this carbon, right? So this is my intermediate after step 2, right? Afterwards, the altered electronic configuration is restored to the positively charged carbon in the carbocation by transfer of electrons from a CH bond, and the transfer of electrons is facilitated by the H2PO4 acting as a base to form this dipentene, which is also known as your limonene, right? Which is a diterpene, right? So the transfer of electrons is facilitated by H2PO4 acting as a base. So by observing my dipentene, I know that it must be this hydrogen that's being deprotonated, right? So since this is acting as a base, right, H2PO4 minus will come in to attack the H, right, and this will come back down to form a double bond here, right, and of course we regenerate my H3PO4. This question will differentiate the A plus and the A's, right? And of course, you can show dipoles as well. So all the partial positive, partial negative, all the partial charges you should show as well. Right. So if you can recall from what you have learned in your bio, right, cholesterols have this kind of structure, right? In fact, your cholesterols are made up of units of isoprene. Do you learn that? Right. So this is your granule, it is made of isoprene units, right? So this is your isoprene unit. Yeah, correct. This is your isoprene unit. 1, 2, 3, 4, 5. So your isoprene units, right? There's 2 for your granule. You can actually functionalize and join them together to form bigger structures, such as your cholesterol, etc. Right? So it's actually very useful. Nature use your phosphate chemistry to join them together, right? And your enzymes are very, very good at directing which part attack which part, right? So for example, like this case, you might think that for the second deprotonation step, you should generate the more stable alkene, which is here. Oops. Right? Which is like that. Because it's tetra-substituted, this is only di-substituted. But enzymes make it such that they can withdraw this H to form the less substituted alkene. Right? That's the wonder of your enzymes. They can catalyze those kind of reactions whereby it's hard to achieve in lab. Okay? Anyways, let's look at question 13. So you just have to follow the instructions. So first step is a SN2 kind of reaction, right? So you will generate this intermediate plus your Cl minus. you can draw in your partial positive, partial negative, right? So after you obtain this, this is followed by a Cl minus acting as a base. So now your Cl minus acts as a base to deprotonate your H. Right? You must be very familiar with these kind of curly arrows really, right? So afterwards, you obtain once again this deprotonated species plus your HCl. Right. Afterwards, a nucleophile substitution on the carbon atom by another Cl takes place. So you have another Cl, right? And you attack this carbon. Afterwards, resulting in the formation of a PO double bond and breaking of a PCl bond simultaneously. So everything is in one step process. So you can just go ahead and break this PCl, and then you form this PO. Right, so this is how your arrow movements should be. It must be simultaneously. Right, so after this reaction, you will have Cl here and this plus your HCl. Right, so just a quick thing to note. You cannot throw in Cl minus and expect OH minus to leave, right? So you're actually using this to first convert your OH into a good leaving group before using Cl to kick this good leaving group out to achieve your product. Okay? So don't worry, for this kind of reaction mechanism, they should always give you these kind of steps, right, to guide you. So next, considering the bonds formed suggests one reason that drives this reaction to completion. You should have learned this already, right? Your HCl is a gas, and HCl bond is quite strong. Apart from that, your PO double bond is also very strong. So this is the thermodynamic driving force. Now for the entropy driving force is quite obvious. 2 species become 3, right? So there's an increase in entropy as well, which makes this reaction favorable because your delta G is less than 0. Okay. And lastly, ethanol can be converted to both ethanol and ethanoic acid. This one you should know, right? State the reagents and conditions. So in order to convert to ethanol, right, you have to use your K2Cr2O7, right, acidified, and then you distill. Right, in order to obtain your carboxylic acid, you just have to, same set of conditions, just have to heat in a prolonged period. Or you use KMNO4, right, either way is fine. Basically the first part is the killer, the second part is a giveaway, right? Then question 14. step 1 and 2, right? Not much of an issue. So you're introducing alcohol. The only way to introduce you're introducing oxygen. So the only way to introduce oxygen from alkene is by hydration, right? So following your Markovnikov rule, the rich gets richer. Your OH should add to the 2OH should add to these two positions. Afterwards, in order to get E, you just have to perform a oxidation, right? Only the secondary alcohol will be oxidized. So for step 1, you will be your H3PO4, correct? And heat. I forgot the exact conditions, right? But it involves H3PO4. Just take note. And then for step 2, you need to perform oxidation. So you can either use KMNO4 or your K2Cl2O7, right? So KMNO4 heat and your reflux, right? Acidified KMNO4 and heat, and you obtain E. The main problem lies with F. So same thing, the first thing to ask yourself is always, of course, count the number of carbon. You realize that the lactone has 1 carbon less, correct? So this step down reaction gives you a big hint that it should be your iodoform reaction, because I won't say only, right? For your iodoform reaction, one key characteristic is a decrease of your carbon. You can call this a step down reaction, right? Compared to your step up reaction, which is basically introducing Cn-. That's your step up, so this is your step down, right? So for F, after I perform this step down reaction, I will have a carboxylate here and an OH, right? So this is your F. Afterwards, you can just throw in corn H2SO4, you will protonate this, and later on perform a cyclization, esterification to get your lactone. Okay? So the problem of this lies in the F, right? So next. Acids reacts with which metals? You still remember the trend, right? They have learnt fleas and cat monkeys and zebra. The metal reactivity trend. Zinc is also quite high, correct? Which means if you add zinc to acid, you will still see reaction. So since phenol can act as an acid, you should react with the zinc as well. So this question is, you can just replace zinc with sodium, right? And so the question is basically asking you to describe how zinc acts as a catalyst for this reaction, correct? And you have learned that if you add sodium, why does it speed up the reaction? It's because you generate your phenoxide, right? So zinc will function the same way, right? It can act as a base to deprotonate your phenol to form the phenoxide before your phenoxide reacts with your acyl chloride. Okay, the concept is the same. Another way you can think about it is that these two, right, if you add zinc, these two can adsorb onto a zinc surface. So the effective concentration is also higher. Okay, this is another way you can explain. And usually people like to use heterogeneous catalysts because you can recycle them easily compared to homogeneous catalysts, right? Because they are in a different phase, you can just perform filtration to remove it, reuse it, right? So this is one example. Right, if you're okay with that, you can do 16. first step, same thing. It's just an acid-base reaction to form this species. To form this species. Afterwards, nucleophilate substitution, and you obtain your G, right? So what type of reaction takes place in step 2? Step 2 is a nucleophilate substitution reaction. Cl is the nucleophile, your OH is the carbon is the electrophile, right? Quite straightforward. Suggest structures for HMJ. H, by using KCN, both of the Cl will be converted to Cn, right? And by performing reduction, both of them will be converted to amine, right? Remember to draw a number of carbon correctly. 1, 2, 3, 4, 5. And H2, H2N, right? You should have an increase of number of carbon by 2. Yes, okay. And next, for J, you use H3O+. This is the conversion to your carboxylic acid, right? Now if I tell you J loses water immediately to form another cyclic compound, okay, what can you propose? Right, if J loses water spontaneously to form a cyclic compound, right? Let's say I call it K. So what is the structure of K? So this is your J, this is your K, correct? I told you that you lose the water. So the water that's lost is just this OH and the H, and you just join them together to form an ester. Right, a 7-member ring ester. 1, 2, 3, 4, 5, 6, 7. And this is your K. Right. And such such cyclizations are actually observed before, right? So don't be surprised if, let's say, you see reactions whereby it involves reactions that you've never learned before, right? Because it's pretty much the only cyclic structure that you can form by losing water. This is known as an anhydride, by the way. Okay, last question. Which chapter are you at now?
Carboxylic acids.
Haven't finished yet?
No.
I finished all of organic chem, then we finished electrochem also.
So now starting on.
Periodic table.
Oh, okay. That means you all haven't do nitrogen compounds. Okay. Then in that case, you can skip question 4. Right, you can try question 4, part 4. So for the first part, reagents and conditions is just Cl2 and AlCl3, or your FeCl3, right? Quite straightforward. If you were to look at step 2, right, if I ask you to classify step 2, how will you classify it? What kind of reaction will it be? Electrophilic sub, right? Just that you're using N2O4 as the reagent instead of your HNO3. And then for step 3, you are using OH minus. So what kind of reaction is this?
Nucleosub.
Right, this is nucleophilic sub. Don't just see ring then you electrophilic sub, right? So now before we go into the other steps, let's look at step 3 in detail, right? Step 3 is very strange because you have learned that nucleophilic substitution doesn't occur on chlorobenzenes, right? But how come for this reaction it happens? Now if you can recall what we have discussed just now, right? If let's say I have nitrobenzene, I can draw partial positive at these 3 positions, right? Now if let's say I have 3 nitrobenzenes, right? This partial positive is going to be even greater, right? Because all of them reinforce each other. So the partial positive is going to be very, very great, right? On top of that, you have a Cl. Remember for a nucleophilic substitution, you always draw the delta minus and delta plus, like that, right? Which means this on top of the effect caused by these 3 NO2, you still have the electron withdrawing effect caused by Cl. So this is very, very positive, right? It's so positive that this effect overwhelms whatever that we have discussed on why chlorobenzene doesn't undergo nucleophilic substitution, right? So therefore, nucleophilic substitution can occur because of all of these favorable conditions, right? Last time we say why it didn't occur is because simply there's only one Cl, right? So the delta plus is very, very small. There's no driving force, right, for this reaction. But for this, there's a clear driving force. So therefore, nucleophilic substitution can occur for this case, right? Precisely because of these 3 electron withdrawing groups. In fact, NO2 is the strongest electron withdrawing group, right? You can go back to your arenes and see the trend. NO2 lies on the extreme, right? So therefore, this makes your nucleophilic substitution, which was previously unfavorable, favorable. So you can actually use your OH minus to do an attack, right? So now the question is, does it do SN1 or SN2? If you look at the intermediate, okay, that's drawn. Can it be a SN1? It cannot be SN1, correct? Because SN1, for SN1 you shouldn't have a Cl connected there, right? Can it be a SN2? You can't have an SN2 because SN2 aren't supposed to have intermediates. So in fact, this is neither an SN1 nor an SN2, right? You have learned SN1 and SN2. Who knows there might be SN3 one, correct? You only learn these 2. In fact, this is neither. This is known as a nucleophilic, right, aromatic substitution. Remember, you have learned your SN1, you have learned your SN2. This abbreviation is known as SNAR, right? Just for information, right? So this is another kind of nucleophilic substitution reaction, although it's still called nucleophilic substitution, right? Because this is the main point. So for this nucleophilic aromatic substitution, what it will do is that this OH, right, will come in to do the attack, okay? To form this species. ClOH, right, with a negative charge. And then what happens next is the formation of the kicking out of this Cl to form back this aromatic ring, right? So instead of always drawing everything that drops down into the ring, we draw from the ring, comes back, and kick this out the other way around. Okay? So this is like the reverse of your electrolyte substitution. And then you will obtain your picric acid. Right? So question 3 asks you to suggest a reason why this anion intermediate can be formed. Same thing, you have your NO2 as electron withdrawing groups, correct? So they can actually disperse the negative charge and stabilize the anionic intermediate. This is also another reason why these can undergo nucleophilic substitution. Right? In fact, there are of course other kind of nucleophilic substitutions. For example, nucleophilic acyl substitution. There's another kind. Right? Just that you learn these two as the only two examples for nucleophilic substitution. And next, state the reagents and conditions for step 4. After you have learned nitrogen compounds, you should know the reaction conditions. Just take note of the NO2 being converted to NH2, right? This is quite a specific set of reaction. You have to use tin, or some of you learn granulated tin, with your HCl. This is the first step. Second step, NaOH, right? You will learn this in nitrogen compounds. So for the first step, right, it converts this into this NH3+, right? And the second step, NaOH, is responsible for deprotonating the ammonium salt, converting it to amine, right? So in the process, you also deprotonate your phenol, because the phenol is acidic. So step 4 is just these two sets of conditions, right? And next, deduce a structure for compound M. For compound M, right, you have to rationalize which one is more reactive. This is quite a common reagent, right? So if you throw this into this, right, you have a acyl chloride here and you have a CCl here, right? So comparing these two, these will be more nucleophilic because there's a negative charge. So the more nucleophilic one will react with the more nucleophilic side, which is this. This is more nucleophilic, right? So then you will form a ester product for this side. Afterwards, based on the formula for compound M, you notice that there's no Cl left, right? So this must have reacted with this CCl under a nucleophilic substitution reaction, which is your SN2, right? So you just have to draw this properly. You have a 1, 2, 3, 4, 5, 6 member ring, right? And this is your compound M. And for the answers, right, this answer is also accepted, right? So either one, but I would prefer it to be here since this is more nucleophilic, right? But either one is accepted. Okay. This is for next time. Go back and take a look. You can attempt the questions if you are free. I would say that the most difficult parts of your organic is this chapter and your halogen derivatives. These two chapters. Right? That's where there can be a lot